This is a stress strain curve for Polymaker PLA Pro. More on that later in the video. Welcome back to Hoffman Tactical. In today's video, I'm going to be sharing the results on a brief study I did on a nylon. The goals of this study was to understand how moisture in the atmosphere, annealing, and oil annealing affected the tensile strength and the stiffness of nylon. The nylon I'm using in this video is the Taulman Glass Fiber Nylon. I'm not sure the exact makeup of this nylon. It appears to be a nylon 6 or nylon 6 blend by the way it performs in tensile testing and the way it absorbs moisture. The testing I did was all tensile testing. I printed the samples on my Prusa MK3 3D printer horizontally on the bed, and I used enough walls to make sure that all of the lines were aligned in one direction so that layer adhesion or interline adhesion was not a factor. So what we're testing in this video is we're testing the absolute material strength of the filament and not just layer adhesion. I printed out a total of 18 samples and I put them right into my dry box after they were done printing to make sure that they stayed dry. I took the samples, divided them into 3 different sets, so a sets of 6 samples. One of the sets was kind of the control set, and I didn't process it at all. I left it raw, just like it was off the printer. The second set, I annealed at 185 degrees Fahrenheit for 2 hours in hot air, basically in my filament dryer. Then I allowed it to cool down to room temperature and popped it right back into my dry box. The next set of samples I processed a little bit differently. I placed them into an oil bath, annealed them for 2 hours, just like the other samples, but this time in the oil bath. I then let them cool down to room temperature gradually, and I allowed them to sit in the oil bath for an additional 24 hours to absorb oil. The idea behind the oil absorption is that the oil will fill into the nylon, it'll take the place where the water would be, and it'll prevent water from absorbing into the nylon and making it softer. So the idea is that the oil will prevent water absorption or reduce water absorption to keep the nylon stiffer and stronger. We'll find out if it actually does that. I then took my samples, which are now all back in the dry box, and I took each of these sets of 6 and I split them into 2. So I now have sets of 3. Half of these samples I left in the dry box. The other half I placed on my windowsill for 2 weeks at ambient conditions to absorb humidity. And here in Tennessee, the humidity is quite high this time of year, probably over 70–80%. So this is, I think, a realistic test of what a real-world part would be exposed to in the atmosphere. After the end of 2 weeks is I have 6 different sets of samples. Each one of these sets is broken up into 2 different halves. Half of them are, the 9 samples are moisture conditioned. They've been out in the atmosphere. The other half is still bone dry in my dry box. And then of the bone dry samples, one of them has been unprocessed, one of them has been oil annealed, and one of them has been air annealed, and the same goes for the moisture conditioned samples. So I now have 6 different sets of samples which I can test to see how moisture and the different types of annealing affect the strength. The oil I used for the test was a 5-weight general purpose machine oil. A thinner or different oil may perform quite a bit better or worse. I'm not sure. This is the oil I used in the shop and I had it readily available. Once all the samples were printed and conditioned, ready for testing, I used my homemade tensile tester to test them. That basically involves putting the samples into the jaws of the tester. The tester then pulls the sample very slowly until it breaks, and the profile of force it took to pull that sample is recorded on a graph. Now, I don't have a strain gauge on my tensile tester, unfortunately, so I had to estimate the strain based on how far the machine had pulled the sample. And while this is probably pretty close, it's not going to be perfect, and it's going to have inaccuracies in it. So keep that in mind throughout this test, that the strain values and Young's modulus numbers should be used for comparison purposes on tests I've done with my machine only, and you probably shouldn't compare them to other values because they're probably not that accurate. After all of the nylon samples were tested and I had recorded the data, I also took a set of 3 samples from PLA Plus that I had printed. It's the Polymaker PLA Pro to be specific, and I tested those. I'm kind of using those as a benchmark for a plastic which is stiff as it needs to be and as strong as it needs to be to make a reliable, functional, for the great majority of parts out there. Heat resistance obviously is a problem with PLA Plus, but we're just looking at the mechanical properties in today's video. We'll be using those throughout this video kind of as a comparison benchmark for how the nylons performed. If you're interested in more details on my tensile testing setup and the specific way I test my samples, check out some of my older videos or let me know down in the comments if you want more details, and maybe I'll do a video on it in the future. One thing you may have noticed is that for each set of conditions, I have printed 3 different samples, and I did that for consistency so that if one sample had something weird happen to it, the other 2 samples would still be good and I could see that something happened and I could know to retest. In this test, all the results were very consistent. The 3 samples were all very similar. I've added error bars to all of my my charts so that you can kind of see what the standard deviation was on each set of 3 samples. If you're wondering why I printed 3 samples, that's why. Now we'll jump into a little bit of terminology. If you're already familiar with all these terms mean that we're going to be discussing, feel free to skip ahead to the actual test results. This is a stress strain curve. The vertical axis right here is stress, and stress is measured in force per unit of area. It's basically how much force is being pulled on a particularly sized sample. This is in pounds per square inch. The bottom down here is strain. Strain is how far that sample has been stretched. At a strain of 0.25, your sample is now 25% longer than it was when it first began. So the very peak up here at the very top, that's the ultimate tensile strength. The ultimate tensile strength is the maximum amount of force the material will withstand at any point before failure. This is called the elastic deformation region. So in this area, the sample is acting much like a spring, and instead of being permanently damaged, it's just kind of stretching out, and if you were to release it, it would spring back. You'll notice on our graphs, the area down here has this weird little curve to it, and it's not quite coming down to the origin like it should. That's because of inaccuracies in my testing setup. The area right here is the plastic deformation region, and in that area, the plastic is, the actual molecules of the plastic are torn apart from each other, and the part is permanently damaged. After your line starts to curve, and I'm going to skip to another graph to show you this a little bit better. We have a nice straight region right here. This is the elastic deformation, and then we begin to curve. This curve is the material actually kind of beginning to tear apart. It's beginning to grow in length in an irreversible way. And then at some point we reach the maximum amount of strength. The material even has been damaged up to that point, and then we actually have a failure at the end. The slope of that, basically the amount of force per the strain, that is something called the Young's modulus, or the modulus of elasticity. What this is this is a unit of stiffness. We can see that the line right here, the steeper this line gets, the greater the slope will be, which is the rise over run. At a very, very steep line like this would mean an extremely stiff material. A very, very shallow line would mean a very flexible material that's not stiff. This curved region I said was the material being permanently damaged, and the straight region right here was the material being elastically deformed in a reversible, not permanent way. The area where we transition from elastic to plastic deformation, that point is called the yield point, and that is important because that is how much stress you can apply to the material before it actually fails. The yield point can be kind of hard to pinpoint on materials like this where you have a very gradual transition. There's the 2% method, there's different methods. I've done very best I can to pull out the yield point on these graphs, and I've charted it right here for the different test samples. That is the 3 basic terms you need to understand. We have the ultimate tensile strength, which is the peak force it'll take. We have the elastic modulus, which is the stiffness or the slope of this initial elastic deformation area right here. And then we have the yield point, which is where we transition from elastic deformation to plastic deformation. Okay, now that I've scared away all of my less interested viewers, we actually are now down to the base audience that I have viewing, and I can kind of go back to my normal self and stop being so robotic. Okay, now we can actually have some fun. Let's look at the test results. This here is where I plotted the ultimate tensile strength for all the different samples. This is the dry nylon that was kept in the dry box. This is the wet nylon that was allowed to absorb moisture. And then this guy over here at the end is the PLA Pro from Polymaker. I've added some little error bars to these graphs, and this is the standard deviation, so you can see how much these samples deviated. The deviation is really low. I was pretty impressed, and the Polymaker PLA Pro had basically no deviation. It was super consistent. Looking at this data here, I've pulled a few things out. This is the glass fiber nylon from Taulman 3D, and this is incredibly impressive tensile strength. We're looking at like between 12 and 14,000 pounds per square inch, which is really, really, really strong. That is really impressive. Compare that to Polymaker PLA Pro around 8,400 way down here, and that's plenty strong for most applications. When dry, the raw nylon saw a nice jump in strength. It went from 12,800 up to a little over 14,000 pounds per square inch when we annealed it. The annealing of the nylon increased the tensile strength. The oil annealing also increased the tensile strength, but not as much as the air annealing. This leads me to make the conclusion that the oil is degrading the tensile strength of the nylon in a similar way to water, though not as much. So over here, you can see the raw nylon saw a massive drop in tensile strength. It dropped down to 1/2 its tensile strength, basically less than 1/2. It's ridiculously weak now. It's down to around 6,000 pounds per square inch, which is really weak. That's in the level of ABS or PETG. That's not good. That's quite weak. The air annealed nylon, once again, a little bit stronger. It's actually about the same ratio as it is when it was dry. The annealing is still benefiting us. What's really interesting here, unlike when the nylon was dry, the oil annealing is actually stronger than the air annealing was. So when it was dry, the oil annealing was weaker, which leads me to believe that the oil is making it slightly weaker and softer, just like water. When the oil is after it's been conditioned for 2 weeks in the atmosphere, the oil annealing is now the strongest of the three. The reason this is so critical is obviously my assumption that the oil was going to prevent moisture absorption is true. That even though the oil is not making the nylon stronger by itself, it is now stronger because it prevented the moisture from being absorbed by the nylon. Rather than being totally saturated, some of those little spaces inside the nylon, instead of being filled with water, are now filled with oil, and the oil does not degrade the nylon as much as the water does. Looking objectively at this, the oil-filled nylon is not that much stronger, and it's still significantly weaker than the Polymaker PLA Pro, which is unfortunate. One last thing to touch on here is that the oil annealed nylon is only 87% of the strength of the Polymaker PLA Pro, so it's almost there. Now this moves us right into our next graph, which is the Young's modulus. Here you can see that the oil annealed nylon is only 79% of the Polymaker PLA Pro, which is significantly less than it was with the tensile strength. Looking at this, the Polymaker PLA Pro actually, looking at our Young's modulus, everything looks pretty similar here, except the dry nylons are very, very similar. There's very little discrepancies, and the oil annealed actually comes out very, very slightly stiffer than the air annealed, even though it was slightly weaker on the ultimate tensile strength. And then if we come over here, we can see that the PLA Pro has gotten a lot further ahead and is now, instead of being way down here, like 60% of the strength of the dry nylons, it's now like 90% of the stiffness. The PLA Pro is actually a very stiff material, and this is kind of the benchmark. That's the stiffness we're going for here. The raw nylon is 62% as stiff compared to the Polymaker PLA Pro, and the oil annealed is 79%. So that is a significant increase, but still not enough because we really need as much as the Polymaker PLA Pro here. Looking at the Young's modulus, we come to a similar conclusion as we did looking at ultimate tensile strength, and that is that, yes, the oil annealed nylon does increase the stiffness after moisture absorption. Plain annealing also increases the stiffness over both dry and raw nylon. And then I'm not sure why the oil annealed nylon, in this case with the dry nylons, was slightly stiffer than the air annealed, but they're so close I'd basically call them the same. I approximately looked at all of these graphs, these stress strain curves, and did the best I could to pull out yield point. And I've here compared the yield point to the ultimate tensile strength. So with our dry nylons, they're not particularly ductile, and the yield point of the material is not very far behind the ultimate tensile strength. Interestingly, the raw nylon had very little yield at all, and the air annealed and the oil annealed nylons had a bit more yield. And you'll see this when we start looking at the stress strain curves. So that's kind of interesting that after annealing, they actually became slightly more ductile, and there was more plastic deformation before failure. What really starts getting bad is when we jump down here and look at our wet values compared to the PLA Pro. So down here, after moisture absorption, there is a lot of plastic deformation. Our yield strength on the raw unannealed nylon drops down to 4,500 psi, which is ridiculously low, not strong. At 4,500 psi, we're now beginning to get failures. That's really bad. Looking at air annealed, that jumps up to 5,400, which is a significant increase, but still pretty bad. Oil annealed is significantly better, and we're up at 6,300 psi for the yield point, which, while still being really bad, is way better. Comparing all of these to the PLA Pro actually is very stiff right up to the point that it yields. There's very little of that plastic deformation zone, which is actually a good thing. And the PLA Pro is almost the same on yield and ultimate tensile strength at 8,100 psi. So we're looking at 7,200 compared to 8,100. The oil annealed is beginning to get up there to a practical level of strength. Not quite though, and it's still lacking significantly in the stiffness department. If we look at the Young's modulus again, we're still way behind on stiffness. Let's jump into our stress strain curves real quick and just kind of go over these and just emphasize what we've been seeing so far. This guy right here, the stress strain curve for dry unannealed nylon, it almost looks brittle looking at this chart here, and it has a nice linear elastic deformation area, and then we have a very little bit of plastic deformation, and then we have a nice failure. Air annealed is actually very similar. The oil annealed kind of came out slightly in between the air annealed and the unannealed. Moving on to the wet samples, we have some pretty serious change. You can see obviously our ultimate tensile strength is way lower. We have a small region right here where we have elastic deformation. Very quickly move into this long transition zone where we begin to have permanent deformation, but of necking, the sample actually necks a lot before finally tearing at the end and breaking. And this tear right here is due to the glass fibers in the nylon. If this was just a plain nylon, it would neck for a ridiculously long period of time before failing. So with glass fibers, it makes it a little bit stiffer and you lose some of that necking at the end. Air annealed sample, we already see a significant increase. Unannealed sample right here almost went to 0.45 on the strain scale. The annealed sample went to below 0.35. It broke off sooner, and you can see that the slope right here, this is stiffer and our ultimate tensile strength is higher than it was over here. That trend continues with the oil annealed nylon. We are significantly steeper here, and that makes it stiffer, less plastic deformation, and it's breaking off sooner. The trend here can be clearly seen that our sample is getting stiffer and stronger and more like our dry sample. That leads me to believe just plain annealing increases the strength of the material by crystallizing the nylon, but by itself it doesn't do that much good. And if you combine, that's right here, the plain annealing. And if you combine the plain annealing with the oil is preventing moisture absorption and getting you closer to the dry nylon, which has actually pretty good properties. And then we move over to the Polymaker PLA Pro, and this is kind of an optimal material as far as the stress strain curve goes. It's pretty nice, extremely linear, elastic deformation zone. And then at the end of that, it breaks, it begins to neck, plastic deformation, a nice crisp transition point right there. We get plastic deformation, we get necking. And the necking is actually caused, it's a rather complex phenomena in different materials, but in this case, it's actually caused by when the material begins to plastically deform, there's a lot of friction and heat created, and that heat softens the PLA plus enough where it begins to neck. So if you cool it down and don't let that heat build up, you'll drop off right about here pretty sharply, similar to the nylons. Kind of interesting, but that super nice straight line there and then a drop off is very reminiscent of what our dry nylons look like. And this is actually kind of what we're going for, a nice stiff material with a nice drop off. These guys right here, the wet nylons, are closer to rubber than they are to an actual solid stiff material. This makes them not very practical for most real-world applications like lower receivers or this new super safety I'm working on, which is why I'm doing this research. I'm trying to find a new material that stays stiff and is abrasion resistant. So if you enjoyed this kind of video, be sure to like and subscribe for more testing videos of this sort, as well as other 3D printed and as well as firearms related content. So if you're looking for copies of the graphs and charts and the data I used in this video, head out to hoffmantactical.com. I will do a brief blog post with detailed copies of each chart and graph so that you can look at it and come up to whatever conclusion you want. I'll also include a brief description of how I conducted my tests, so for purposes of documentation. Definitely check that out if you're interested in pursuing this subject a little bit deeper. Okay, let me briefly summarize what we tried to learn in this video. There were three main takeaways. Number one, the moisture seriously degrades the tensile strength and the stiffness of the nylon to a level where it's not really practical for many parts anymore. I like to use the PLA Plus or Pro PLA, or in this case, Polymaker PLA Pro, as a baseline strength for materials. Because most parts are designed for a PLA Plus or a PLA Pro, that's what I design parts for. That's kind of a standard which we know works. If you go below that, you risk having parts fail. If you go above that, that's awesome. However, in this case, the moisture conditioned nylons were all significantly less stiff and weaker than the Polymaker PLA Pro, which is not good. The second takeaway is that annealing the nylon does make it stronger, both when it's dry and wet. In my last video I did on testing nylons, I did impact testing, and we found that after annealing, this was with wet nylons, after the nylons were annealed, they became less impact resistant, and I postulated that they would have become stronger and stiffer, and that turns out to actually be the case. Annealing makes your nylons less impact resistant, but stronger. The third main takeaway is that the oil absorption into the nylon actually improves its resistance to moisture. What I think is happening here is the oil is being absorbed into the nylon, and it's kind of impregnating the nylon molecules with oil that is preventing a certain amount of water from getting into the nylon. The oil is getting the nylon and it's blocking water from getting in there because the oil is already taking up space. And this is an assumption I am making. I could be wrong here. If you have a different idea, definitely leave it in the comments below. Moving forward, what am I going to do next? So first of all, I'm actually going to do the exact same test with the Polymaker PA12 carbon fiber nylon. PA12 is significantly less hydroscopic from everything I've read. Nylon 6 is very hydroscopic. That's what the Taulman Glass Fiber Nylon is based on from everything I can tell. The Nylon 12 should be much stiffer after absorbing nylon. However, Nylon 12 in general is weaker than Nylon 6. It's going to be a super interesting comparison, and I am interested in what the results of that are. Another thing I'm going to want to do at some point here is I'm going to redo this test with the oil annealing, but instead of just annealing the parts in the oil for 2 hours and then letting it soak for 24 hours, I'm actually going to anneal them in the oil at elevated temperatures. I'm going to place them into a pressure pressure vessel at elevated pressure above atmospheric pressure for a significant period of time, like several weeks, and see how much oil we can force into the nylon and see how that affects its tensile strength to dry, and then try to moisture condition it and see what it looks like after that. If we can get enough oil into the nylon and the nylon does not degrade in strength because of the oil that much, and it prevents moisture absorption, that's a huge win. That means that we can use these extremely abrasion resistant nylons and still have them strong and strong and stiff, which is important. Hope you enjoyed today's video. I'll catch you again next week. Thanks so much for watching.